was pretty representative of what we covered, maybe right down the middle. Nothing too hard. There might have been a couple easy problems on there, but hopefully nothing too terribly difficult. If you bombed the test, it's not the end of the world. So if you got a 68 or something like that, and you're hoping to get an A in the class, it's still possible. I will replace your lowest exam score with your final exam percentage. So if you got a 68 on this and you pull a 95 on the final exam, I'll go back and I'll replace that 68 as long as that's your lowest exam score with the 95. It's like it never happened. Okay, so you get one poor test score that you can recover from. After that, they're stuck there. They're going to count. What's that?
That's if you do well on the final.
And that only works if you do well on the final. So if you don't do well on the final, you're in the same boat. Okay? All right. So let's run through and let's take a look at the starter question. And if you've been paying attention, and I was pleased with the number of people who were able to find formulas for the derivative and kind of did it in general rather than several of the problems on the last test. You actually could have plugged in a number to start with, and that makes it a little more numerical, but maybe not quite as valuable. So what we want to do here is, given this function, square root of x, we want to find f prime of a. So here's what I'm going to do. I'm going to define f prime of a as the limit as h approaches 0 of f of a plus h minus f of a over h. And then I'm going to plug in these values into that function. So this is going to be the limit as h approaches 0. This is going to be the square root of a plus h minus the square root of a all over h. And then I'm going to try and evaluate this by substitution, but of course I can't do that because the denominator is going to be 0. So what I do is, okay, we're going to multiply by the conjugate. We're going to rationalize the numerator. So this is going to be radical a plus h plus radical a plus h plus radical a. And here's what I end up with. I've still got a limit as h approaches 0. The numerator is now a plus h minus a. So the numerator is now just h. And the denominator has an h times the square root of a plus h plus the square root of a. So I can cancel the two of those, and this is what I'm after. I'm after the limit as h approaches 0. 1 on the top, square root of a plus h plus square root of a. And the only variable here, the only thing that's changing in the limit is the h. So the numerator is a 1. That doesn't have an h in it, so that's just going to be the square root of a. And what happens if h approaches 0 on this expression right here? You get the square root of a. So I'm going to have 1 over square root of a plus square root of a, which is going to be a 1 on the top and 2 square root of a on the bottom. Okay, and there were several people that approached problems. I don't think we didn't have an example. Yeah.
Sorry, I did it with the other one as x approaches a,
Mm-hmm.
and I think it was a little bit faster for this particular problem.
For that particular problem, because you're good at factoring, right?
Yeah.
Yeah. So Juan's trying to point out this. He did it this way. Square root of x minus square root of a over x minus a, and he said that was faster. And it is, but only if you know how to factor the two of these. Okay? You can factor the denominator, and it's a difference of squares. That's a perfect square with the square root of x. That's a perfect square with the square root of a, right?
I also just did the conjugate, and it pretty much ends up being the same.
Okay, yeah, that works too. Yep, very good. Yeah, lots of different ways to do this. That's why it's nice to be good at algebra. Okay, so if you take a look at this next paragraph, this is kind of a summary of the stuff that we've gone over before. So it says, in Chapter 2, we introduced the concept of a limit, and we showed how limits can help us find instantaneous rates of change. And what we started with was finding blank rates of change. What did we start with? We started with average rates of change. And on a graph, the average rate of change, we could represent as the slope of the secant between 2 points. Okay? The blank rate of change can be represented by the tangent line, the slope of the tangent line. And what's that? Instantaneous. Instantaneous rate of change. The limit of the slope of the secant, as the points move closer and closer together, so the slope of the secant gets closer and closer to the slope of the tangent. So in the same fashion, if I take the limit of the average rate of change, That's going to be the instantaneous rate of change. Limit of the slope of the secant gives you the slope of the tangent. Limits of the average rate of change, that's going to give you the instantaneous rate of change. And then we also learned that we can use this word derivative to describe the instantaneous rate of change of a function. Okay? And what we're going to do to finish up chapter 2 in 2.8 and in all of chapter 2 is we're going to be looking at the derivative as a function. The derivative as a function. And as we've mentioned before, so hopefully this is just repeat and kind of reiterating what you've already figured out, the derivative is basically a formula. It's a formula that gives us the instantaneous rate of change. Okay? So in other words, it gives us the slope of the curve at any point. And remember we talked about rate and slope and derivative. We want to make sure that we're thinking of those all the same way. So if we say slope of the curve, or somebody says slope of the curve, or they say slope of the tangent, okay, or they say the instantaneous rate of change, we're all talking about the derivative, and those all mean the same thing, okay? It's just a question of whether we're thinking just strictly graphically or thinking about it in terms of a function and that sort of thing. So here's the definition of the derivative that we're going to use for the most part. Again, this isn't the only definition. It says the function f prime of x equals the limit as h approaches 0, f of x plus h minus f of x all over h. All really familiar. We're saying that is the derivative of f as long as that limit exists. If that limit doesn't exist, then it doesn't have a derivative, or at least at that particular point. Okay? So if we can find the derivative of a function, then we say the function is, here's the word, differentiable. So if I say I've got a differentiable function, that means you can find the derivative. If you can find the derivative, that means it's a differentiable function. And there are actually 3 different forms of the derivative, and I'm just going to go over these really quickly because we've seen at least 2 of these before. This is called the difference quotient. So this right here, it's the definition that we've said comes up most often. It's the definition that's used in this little box up above. And we're literally doing this. We're looking at the 2 of these things. This one's located at x, this one's located at x plus h, and we're computing the slope. The run, the difference in the x coordinates is h. The difference in the y coordinates is f of x plus h minus f of x. And then we take the limit as, again, we're controlling this distance right here. We're taking that distance right there and we're shrinking h. We're letting h approach 0. Okay? So that we've seen before. Okay, this one is called derivative at a point. Okay, it's also a difference between y coordinates over a difference in x coordinates. This x or y coordinate is f of x. That one's f of a. And the denominator would be the difference in the 2 x coordinates, x minus a. And we're taking the limit as x approaches a. So this is, in very generalized terms and in generalized pictures, what we talked about in the last chapter. Okay? Okay, this one is called the symmetric difference quotient. Symmetric.
And what is this one?
Okay? And this one is good. We don't use this very often. This one, the idea behind this is very good because it's good if we have data. We're not going to make it this complicated if we're going to derive a formula for a derivative. Okay, but if you've got data, here's the idea. This is the point where we want to find the derivative at x. So what we do with the symmetric difference quotient is we go forward a little bit, we go forward h, and we go back h. So that means this point right here would be f of x plus h. This point right here would be f of x minus h. So we're going a little bit on the left and the right of each side of the point of interest where we want to find the derivative. And then we do the same thing we did before. Calculate what the slope would be. Well, it would be the difference between these 2 y coordinates. So that's going to be f of x plus h minus f of x minus h. And then how far is it from here to here? What's the difference in the 2 x coordinates from here to here? Not just h. We went forward to h and we went back h, so it's going to be 2h. But we're going to control how far apart these are by controlling what h is. So it's still the limit as h approaches 0.
So this gives, so it's forward and backwards. Are we going to get the instantaneous, what are we going to get from it?
Well, if you think about it, we are, because what's going to happen as h approaches 0 is these points are going to get closer and closer to the point of interest, closer and closer to x. That's still going to approximate the tangent line. This is much more complicated than this one right here. Everybody agree with that? So we don't use this in practice very much, but keep in mind why we might want to use this for data, like if we didn't actually have a function. This would be a mess if we were doing it with a function. If we have data, think about what's happening here. We're considering the behavior, or in other words, the slope on the right side, and we're considering the slope on the left side. So remember that heartbeat example? The best thing to do, if you want to know what the heartbeat is at 42 minutes, let's not do from 36 minutes to 42 minutes, or let's not even do from 46 minutes to 48 minutes. How about we do from 44 minutes to 48 minutes? And that would be a good estimate, or sorry, we're doing 42. So 40 to 44 would be a good estimate for 42. Okay, so symmetric on either side.
Okay, so what's the, if it's, wouldn't it give us the same tangent though?
Yes, it would. And that's the point. Okay, all of these will produce exactly the same thing. This one right here is a good idea for data. I just want you to keep that in mind. If you're given data, it would be what?
When you don't have a function.
When you don't have a function. Yep. Yeah. I mean, if you had your choice, we're going to use number 1, maybe number 2, probably not number 3 if we're given a function. Okay? Anything else? Okay, so a little bit more vocabulary. The process of finding a derivative is called differentiation. Differentiation. So if I say, hey, do the differentiation on that, that means go find the derivative on that. Okay, and then there are lots of different types of notation that we can use for the derivative. Okay, we've seen f prime before. If we replace an f with a y, we'd be talking about y prime. And then we're going to use this notation right here quite a bit. This is said dy dx. This means the derivative of y with respect to x. Okay, and if I had to say which ones we're going to use most often, they're these guys right here. So let's talk about them for just a second. The derivative of y with respect to x. This would be the derivative of f with respect to x. So it means we've got a function of x, and we're going to find the derivative with respect to that particular variable. This right here is written out front. So we say d dx, or the derivative with respect to x, of f of x. Okay, now these you don't see them very often. Okay, I just want to show them to you in case you do happen to encounter a book that shows you those. If you see a big capital D in a calculus book, it's probably talking about the derivative. Okay? The point here is each one of these is what we call an operator. It tells us to do something. And what it means is find the derivative of f, find the derivative of y, find the derivative of y with respect to x. A little bit more specific way of saying it. Find the derivative of f with respect to x. Okay? This looks a little bit more like an operator. It's saying find the derivative with respect to x of whatever comes after this. Okay? So we just want to be aware of the different types of notations, and you'll get used to them because we'll use them so much. Okay? Now let's look at this guy right here, dy dx. It looks like a quantity, and you could, or a fraction, and you could think of this as a fraction, the difference in the y over the difference in the x's. I mean, it's kind of like a fraction, but we're not going to treat those things, the difference in y over the difference in x, as separate quantities until a little bit later in the book. Okay, we'll learn about something called a differential. Okay, for right now, this thing only exists in the limit. So let's talk about what we can do with a derivative for just a second. And I think I've mentioned examples like this before. Derivatives are extremely powerful. They're used all over the place in science and economics and different things like that, because they tell us a huge amount about the graph. Up until now, we were only able to answer things like this. Like if I said P of 1 is 1,000. Well, in this particular example, P of T is a price function. It gives you the price of a stock on any given day. So if you plug in what day it is, it will tell you the price of the stock. So if I plug in day 1 like it is right here, how much is the stock worth? Okay, 1,000. $1,000. Okay, that is a pre-calculus type piece of information. That is one piece of information that you could get from the graph or from the function. If I then add to that something like this, put yourself in the position of owning this stock. This says P prime of 1 is 20. This is a derivative. This is a rate of change. So the way we'd graph this type of function, we've got the time here in days, and we've got this right here in dollars. So if I were computing slope, this would be dollars, and this would be days. So this right here represents $20 per day, and it's positive. If you own that stock, that's a good thing. It's worth $1,000, pre-calculus piece of information. Its rate of change, its instantaneous rate of change on that day is it's going up $20 per day. Different piece of information here. What if P prime of 1 was negative 50? Again, the units here are dollars per day. This is bad news. It's going down. Okay? So do you see how calculus, do you see how rates of change, how derivatives add another layer of information that we can get from a graph or from a function? Okay? That's where its value is. It tells us what the rate of change is. Okay? Now, you've got some problems on your assignment where it asks you to approximate what the derivative would look like. So we're going to take this very familiar function right here. Y equals x squared. And we're going to estimate what the derivative would look like. Now, when you're given a graph, okay, this is a graph. This is the graph of the function. So this right here is a graph of the function. If I graph the derivative over here, graphically speaking, we interpret the derivative as what?
Slope.
The slope. Okay, so these are the slopes of the function. And this is where people start getting lost in the abstractness of calculus. Okay, we're looking at this, but we're looking at it in terms of, I don't care what the function values are. I don't care that this value right here is 4. I want to know what the slope is there. I want to know how steep the curve is there. Okay, so let's do the easiest one first. What's the slope of the tangent right there at the origin? Right at 0. Slope would be 0. It's perfectly flat, right? So I'm going to come over here, and I'm going to graph what the slope is. The slope is 0. Then I'm going to draw a tangent line right here, okay? Right here. And I'm going to make it look roughly like this. Does that look pretty good?
Yeah, that's pretty good.
Okay, now, this is a graph. Let's estimate what the derivative would be right there at 1. So at x equals 1, what is the slope of the curve? Remember, this is a calculus question. I don't care that the function value is 1. I want to know what the slope is. About 2. Rise 2, run 1. Is that okay? So over here, I'm gonna graph a slope of 2.
At the point 1?
Yep. So these are x values. These are slopes. They're y primes.
Wouldn't the slope just be 1 if it's at the point 1?
No, a slope of 1 would look like this.
Yeah. Isn't that what it should be?
What was the graph?
No, take a look.
Oh, wait, no, never mind. No, yeah.
Is that okay?
Yeah.
Got it. You have to make that transition so you can look at a graph and not think about what is the function value, so you can think of what are the slopes at that point. Okay? Everybody okay with this being 2? Okay, let's do the next most convenient point. Let's find the slope right here. So I'm going to draw something roughly like that. Does that look like a pretty good approximation for how steep the curve is right at that point? It's definitely positive. It's steeper than the one that I just drew right here.
I'd say 4.
Roughly 4. So
Roughly 4,
over
yeah.
1 and up 4. If we graphically represented that, we'd say about 4. Good there? Okay. If this was a slope of 1, if at x equals 1 it had, sorry, I want to graph the right one. You got me messed up then. Okay. So if that was a slope of 2 and that was a slope of 4, if I come over here and I graph the slope right here at -1, what would we have to call that? We'd have to call that a slope of -2. So let's come over here and let's graph -2.
And why would it be? Oh, yeah, but, yeah, you're right.
Okay.
Yeah, I get you.
And at -2, it's going to be this steep, so that would have to be a slope of -4, so we'll graph that one. Okay. Now, let's watch here. We got this graph right here. This is a graph, or at least an approximate graph, for the derivative. These points here represent the slopes on this curve. Okay, what do all of these have in common? As far as the slopes they represent. Not the slope of this line, the slopes they represent over here. They're all negative. Okay? They're all negative. Okay? In fact, I'll write it here. They're all negative. That means this graph always has negative slopes. It's always pointing downward. Okay? This one right here has a slope of 0. It's right at 0. Remember, these represent slopes. These are all negative slopes. That's 0 for a slope. If I have 0 for a slope, what should I see on the graph? Should be horizontal. And does it look like that kind of levels out there for a second? Okay? And what do all of these have in common in terms of the slopes that they represent? They're all positive. So the graph's going to have negative slopes, sloping downward. It's going to have 0 for a slope. Then it's going to be sloping upward because these are all positives. Okay? Now, you with me there? What can you tell me about this slope in comparison with this slope? This slope here in comparison with that slope there. Okay, I'll take that.
Or what?
What about on the graph? He said they're linearly proportional to each other. Okay, they're on a line. It's true, they are. Okay, but again, we're talking about how they relate to over here, the original function. Roughly, what's that slope? No, not the slope of this. What slope does this represent? About 1 1/4, right? Okay, this is 1. 1 1/4 is like this. Okay? That slope right there represents a slope about like this. A slope of about 1 1/4. What does that slope represent?
5.
See, 1, 2, 3, 4, 5. Maybe a little bit more than 5. What does 5 look like? 5 looks like this. This represents a steepness on the original function that is much steeper than this one right here. This one represents a slope about like this. This one represents a really steep slope. And if you think about the parabola, what happens the further we get away from the vertex? Doesn't it get steeper and steeper and steeper? Yeah. Here it gets steeper and steeper and steeper in the positive direction. And what happens over here? Steeper and steeper and steeper in the negative direction. Well worth your time to think about how those things relate to each other. Okay?
So it'd be a straight line if you continue.
Yeah, it's a straight line. Okay? And we're going to prove that it's a straight line right now. Okay? Okay. So then the next thing it says is use the definition to find the derivative at 1. So we're going to go like this. Okay? I'm going to do this part right here. Okay? We're going to use that definition to find a formula for the derivative at any point. So I'm going to do the limit as h approaches 0, f of x plus h, so that's going to be x plus h quantity squared, minus f of x, which would be x squared. Usually a good idea to put those in parentheses, all over h. Many of you did this on the bonus question. Okay? It was even more difficult than this one right here. The only thing you need to be careful of is make sure that you get this right when you square it out. 2xh plus h squared minus x squared over h. I get rid of the x squareds. I factor out an h. I'm left with 2x plus h over h. And then I cancel the h's. Okay, am I going too fast? Are we okay? All right. So now I'm going to bring back the limit. The limit as h approaches 0 of 2x plus h. And what is that limit?
2x.
2x. So that means if you start with y equals x squared, then y prime, or the derivative, is 2x. Doesn't that look like the line y equals 2x?
Yeah.
Yeah, it does. So if I said find the derivative at 1, what do you do here? Plug it in. What is the slope at 1? It is precisely 2. What is the slope? Whoops. What is the slope at negative 2? Negative 4. Okay? Now, this is a really nice graph. Okay? Got little dots on it and everything. Okay? Very familiar function. Just estimating, okay, and the fact that I was here and I've done this about 4 million times is probably a little bit helpful. Okay? But we estimated exactly what it would be here. Okay? So the derivative of x squared is 2x. This is the original function. This represents the values here represent the slopes on the original function. So when I find this point right here, what it means is if you go to negative 2 on this curve right here, what's the slope? Negative 4. Okay? You have to make that transition. Okay, so you've got to spend enough time thinking about it that you understand the relationship between the original function and its derivative. Okay? Any questions? Okay, so let's take a look at a couple of these examples. Oh, let's see. I do want to do this right here because this will help in just a second. It says, please notice what the slope of f of x as we approach 1 from the right and from the left. So if we were to look at this picture right here, think about what happens to the slopes. It's 0 here. I'll zoom in here. So here's our point of interest at x equals 1. The slopes are a little bit bigger, and a little bit bigger. Okay, if we approach it from this side, they're really steep, not quite so steep, not quite so steep. So from either side, it kind of goes like this, gets to a steepness or a slope of 2. And from this side, it starts with maybe a slope of 4, and kind of gradually comes back down till it's a slope of 2. Okay? So kind of consider that for just a second, and we'll get back to that in a minute. All right? So now let's look down below. Okay? So here's some examples. We've got 2 different functions. One of them is kind of weird, just some line segments. And then we've got another one that's nice and smooth and connected and stuff like that. Okay? What we want to do is we want to figure out if these are the functions, if both of these are the functions, what do their derivatives look like? Okay? So these are functions. These down here are slopes of the functions. We're tracking slopes down here. See, we've got an f prime here and a g prime here. So let's look at this first one. Okay, what's nice about the slopes all the way along here? They're all exactly the same. They're all sloped downward. And you'd estimate that it's about -1. Okay, so everywhere over here, we're going to have a slope of -1. What happens in between -2 and 0? Slope is about +1. And what happens here? Slope is negative, and I'd say roughly -1/2. So it looks something like this. Okay? Now, what about right here? And what about right here? Maybe 0.
So on our parabola, when it changed directions, it went to 0.
When it changed direction, it was 0, but it kind of did that in a nice, smooth fashion.
Yeah, it did that slowly.
It did that slowly, did it gradually, right?
Like that.
Did that very gradually. Keep that in your brain for just a second. Let's look at this one right here. These are really steep, what type of slopes? Positive slopes, okay? That's a positive slope, but not quite as steep. That's a slope that's positive, but not quite as steep. What is the slope right here? What's the slope right here? And here? Okay, of all the slopes on a curve, the ones that are easiest to find is when it kind of flattens off. So flattens off like this or like this. So let's take those points and let's transfer those down. At -3, what's the slope?
0.
So we're going to put a point at 0 at -3. Slope at -1 is 0. Slope at 1 is 0. With me there? Okay. What type of slopes, what do these all have in common? All positive slopes. These are big positive slopes. These are small positive slopes. So I'm going to represent that with a big number up here, and I'm going to represent this with a small number right here. Big positive slope here, so a big number, big positive number. Small positive slope here, so a small positive number there. What do all of these have in common? From here to here. They're all negative, okay? Now, it's got a slope about like this here and about like that there. So negative slopes, but not very steep. And then in between, we maybe hit a slope of -1. So let's follow this straight down, and let's do -1 about right there. And not very steep in the negative and not very steep in the negative. See how this is working? Okay? If we made that argument between here and here, what about between here and here? Maybe the biggest the slope gets is +1. And what happens over here? Same thing that happens here. These are small negative slopes and these are big negative slopes. So we'll have a small negative slope and a big negative slope. So here's what it looks like. Let's connect this. These are the slopes of the original curve. These are the slopes of the original curve. So let's take a look. All of these represent positive values. Are all of those slopes positive? Slope of 0. Levels off there. All of these represent slopes that are, follow the graph straight up. Are all those negative? Positive slopes, negative slopes. Okay, see that? Any questions? Oops. Okay. All right. So what I want you to notice is in part A, there were a couple places where, I mean, we could make an argument that that slope is 0, but somebody just as easily could argue, well, why wouldn't it be -1/2? And somebody else could argue, well, it's +1. Notice that the derivative contains a two-sided limit. It doesn't matter if we go to the right with a positive little h or to the left with a little negative h. Okay? It's a two-sided limit. So because this derivative contains a two-sided limit, we want the slopes from either side to agree. If this slope is +1 and this slope is -1/2, do those slopes agree?
No.
Do they transition in a nice, smooth fashion? They don't. So whenever you have something like this, a corner like this, where this slope, where this derivative doesn't agree with this derivative, it's not going to be differentiable there. It's not going to have a derivative, okay? And that's because the original definition contains a two-sided limit. So what that means is for the derivative to exist, the slope needs to be the same on both sides of the point where we're trying to find a derivative. So if we can check from either side, that brings up the idea of what we call a one-sided derivative. A one-sided derivative. So go ahead and flip the page over. And what usually happens with problems like this is we've got a function that's defined on a specific interval, or its domain is a specific interval, okay? So you'll notice this one, we're having h approach 0 from the positive side, so that is going to be a right-hand derivative. We're checking the slope on the right side of the point of interest. If we let h approach 0 from the negative, that's going to be a left-hand derivative, okay? Now, we don't do this very often. Okay, usually we'll end up looking at a graph to figure out what it is. So what I've done is I've taken that graph that we worked on a minute ago, the parabola, and I've restricted the domain to include the endpoints 0 up to 2. So it's not the entire parabola, it's just from here to here. and it says, what is the right-hand derivative at? Well, let's think for a second. What would be the only place that it would make sense on this interval to ask about the right-hand derivative? What is the slope as we approach it from the right? Well, you can't approach 2 from the right. It would have to be what does the slope approach, or what is the derivative as we approach 0 from the right? It approaches that horizontal tangent of 0. And the derivative from the left at 2. So we're checking 2. What's the derivative? What slope does it approach from this side right here? How steep was this? It was 4. Okay. And then it says, would your answer change to the questions above if the interval were from 0 to 2, not including 2? But would it have a point there? Okay. So yes, it would change. Okay. This answer would still be the same. So f prime of 0 would still be 0, but f prime of 2 would not exist. It wouldn't exist because we wouldn't have a point there. Okay. You can't really have a tangent line at a point if you don't even have a point there. Does that make sense? Okay. So, a couple other things. We're kind of cruising through this pretty well, about where I wanted to be. So, if the derivative is defined this way, and it has a two-sided limit, then the only way that we're going to have a derivative is if the left limit exists and the right limit exists, and they agree with each other. Okay? Or in other words, if the slopes on both sides approach the same value. Okay? So, if either one of those doesn't exist, or they don't agree, then we say the function is non-differentiable. So if it's differentiable, it has a derivative. If it's non-differentiable, then it doesn't have a derivative. Okay? And the next thing, please don't underestimate. I've just got some funky drawings right here. This is really important that you understand this. There are 3 ways that a function can fail to have a derivative at a point, or be non-differentiable at a point, is the way we say this. Okay? I would make sure that you know these for the test. Okay? The first way is if we have what's called a cusp or a corner. In other words, it comes to a point. And the reason we can't have a derivative there is, think of these right here. These are all positive slopes. And then in an instant, it flips to negative slopes. There's no way a positive slope is going to equal a negative slope. Okay? So whether it comes to a cusp, so 2 curves coming to a point, or 2 lines coming to a point, okay, the point is we have a point there, we have a corner. Okay, the 2 sides aren't going to agree as far as slope goes. Okay, the next one is vertical tangent. Please don't tell me it's a vertical asymptote. I have this all the time. I'll say, what are the 3 ways a function can fail to be differentiable at a point? And people will say cusp or corner, and then they'll say vertical asymptote. That's not what we're after. Vertical tangent. So the tangent at this point is straight up and down. The tangent at this point is straight up and down. What is wrong with a vertical line as far as slopes go? Slope is undefined. Slope is undefined. Okay? So if you have a vertical line, the slope is undefined. Okay? You could say that it's doing this. It's getting closer and closer to infinity. Okay? But this straight up and down, that's undefined. Okay? And then the last one is called a point of discontinuity. Okay? A point of discontinuity. And that can happen a couple of different ways. We can have a vertical asymptote. The 2 pieces are not connected. We can have a jump. The 2 pieces are not connected. We can have a hole. The 2 pieces are not connected. Okay? So it's not going to have a derivative there if the function isn't defined there. Okay? And the pieces are connected. Okay?
So you have cusp or corner, vertical tangent, and then all 3 laws of continuity.
Yeah, any type of discontinuity is going to make it so the function is not differentiable
So
there.
5 laws.
Any type of point of discontinuity. Okay, we lump them all together. So there are 3 ways it can fail to have a derivative: cusp or corner, okay, vertical tangent, point of discontinuity. Okay, any type of corner here, throw those all together, whether it's curves coming to a point or lines coming to a point. Okay? Any type of vertical tangent there. Anytime the graph does this, goes vertical for just an instant, it's not going to have a derivative there. Okay? And the last one is any type of point of discontinuity. So any type of discontinuity you can think of. Anytime you've got to pick your pencil up, it's not going to have a derivative there. Okay? All right. Any questions? Okay. So we're going to dwell on that discontinuity idea for just a second, and we're going to use this theorem. We're going to prove this. It's actually a pretty nifty and short proof. It says if f is differentiable, so that means if it has a derivative, that means it's got to be continuous. If it's differentiable, it's got to be continuous. If it's differentiable, it has to be continuous, and here's a little proof. Okay? So if it's differentiable at a point, then by definition, this would be true. This limit would exist. It would equal a number here. It would have a slope at that point. You with me there? Okay. Then we're going to rewrite the original function in this weird way. I'm going to take f of x. Notice this is f of x, not f prime of x. And I'm going to write it as f of x minus f of a over x minus a times x minus a plus f of a. Now, why are these things, even though they look ridiculous, why are those two things equal? Cancel this with this to be 1. F of x minus f of a plus f of a. Those cancel to be 0. Isn't this still f of x? It is. Okay? So once I have that expression, we're nearly done. Let's take the limit as x approaches a of both sides here. So I'm going to slap a limit as x approaches a and a limit as x approaches a over here. So the limit as x approaches a of f of x equals, and now I'm going to use my limit laws, the limit as x approaches a, f of x minus f of a over x minus a, times the limit as x approaches a, x minus a, plus the limit as x approaches a of f of a. Let's do this one first. What's the limit here as x approaches a? 0. Is there an x in this expression? Nope. So this one's just f of a. What is this? This is a tough question. And this is one of the things that's tough about watching proofs in calculus, especially differential calculus. If you see something like this, the limit as x approaches a of f of x minus f of a over x minus a, that's the derivative. That's the derivative. That's the definition of the derivative. And it's set up above it's differentiable. That means it has a derivative. So the point is not necessarily what is this or what could we use to represent this. The point is it's differentiable, so that limit exists. It's a number. So what is a number times 0 plus f of a? What's a number times 0 plus f of a? F of a. So this side is f of a, and this side, I didn't mess with that at all. It's just the limit as x approaches a of f of x. And take a look at this right here and go back and look at your notes from 2.5. That is the definition of continuity. Whoops. That is the definition of continuity. The limit exists, and it equals the function value there. Okay? Kind of deep. Okay, we'll stop right there. I want you to think about whether or not the converse of that would be true. If it's continuous, does that mean it's necessarily differentiable? The answer is no. Try and think of a counterexample. There's one in your notes. Okay?